right, welcome back. Today we're extending what we did in the last lecture on deep learning. So in the last lecture we looked at deep neural networks, how they're structured, how they work, which is basically the mathematical foundation, how you can learn the parameters, how you can solve problems with them. And we looked at this simplified version of the XOR problem, and we solved it using gradient descent. So now the XOR problem is not super interesting, right? It's a logical problem. And now we're moving to more interesting applications. And one of them, and this is actually quite exciting for me because this is my main research, is natural language processing. And so this is lecture 11, as I said, deep learning for NLP. When you, or if you do a master's here at the university, I can highly recommend the deep learning for natural language processing course. So this is basically one class that can be extended to multiple ones in this advanced course in the master's program. This is a program that Terry and I are teaching then. So recommended literature is the same as before. Now we're moving more to the right, to the applied part. And first of all, what is natural language processing? For now, we'll say NLP as a short version of this. And NLP is basically a subfield of computer science and also of machine learning and AI. And what it tries to do is it tries to analyze lots of data analytically on the text dimension, and it relies heavily on linguistic and computational linguistic. So here on the right, you can see many dimensions of natural language processing. So it all starts from how humans speak to each other, which is phonetics. So it's the way that we communicate, how I tell you a story now, how you listen to it. And then it goes all the way up to words and phrases, sentences, and you can hire these dimensions. So basically, the way that we approach natural language processing here in the group is starting from words and text. So we're not looking at the dimension of speech first, because once you have converted speech to text, you can analyze it more structured and easier. So this dimension of converting speech to text is something that we're not looking in our research much. But then once you have the text and once you have a structured way of communicating that text in machine-readable ways, that's where we actually have a lot of research on. So that's like looking at phrases and sentences, looking at different documents. How can we categorize documents in specific ways? And so to give you some examples, what natural language processing problems are, or what is the reason why we need natural language processing, is you can say this club is great, but what does it mean? What is this club? It's very highly dependent on the context. So the club can be a club that you go to at night. It can be a golf club. It can be a sports club. It can be multiple clubs. And we don't know exactly what that is until we understand the context in which this fragment, in which this sentence was used. So language is highly dependent on the context, on word knowledge, on idioms, on culture. In different regions of Germany, some things, some words might mean different things. Across countries, that's even more problematic, and so on. So there's many different aspects of language that are ambiguous, that are problematic to understand. And this is the motivation of why we need natural language processing. So some of the things that you might know where NLP is, and NLP is already in our everyday lives, is when you write an email. So when I open up Gmail and I say, hey, Terry, or hello, Terry, I don't even have to type Terry because NLP already analyzes to whom I sent this email. And from past emails, it can see that when I text Terry, I just say, hello, Terry. So when I type hello, it already says, hello, Terry. And then also when I type kindest regards, that's a pattern that is used often. So I don't have to actually type it out. I just press the tab button. If you text on WhatsApp, you know that you often click on the middle of your keyboard because it predicts the next word easily. Or if you mistype a word, it can correct that typing. Then speech recognition, something everyone knows. I have 3 Alexas at home, and many of these assistants are used in our everyday lives. If you use Siri on your phone, or whether you use Alexa to control your environment at home. So speech recognition is one of the applications I think everyone is familiar with. It's actually funny, if you go to YouTube and you type, hey Google, say hey Siri, or say hey Alexa, there's a video where they take 3 of these devices and then they start with one and they communicate in this circle to each other. Question answering is also an application everyone uses probably hundreds of times per day. So when you Google, Googling is basically an information retrieval search. So it searches millions of documents at a fast time. But also recently they have this feature where they answer questions about documents. So when you have a specific, you might get this specific card where they extract a question answer from a document. So if you have here, who holds the world record for eating the most cheesecakes, it understands that as a question and it needs to extract the answer from an article. Sometimes it also matches this to a knowledge base. So Wikidata, for example, is a very large knowledge base from Wikipedia, and it can find related information in that knowledge base. Chatbots, very recently, is a hype. So how can we communicate with systems on a text basis? ChatGPT is a great example for that. So here I asked it to create an outline for our lecture. It starts with machine learning basics. That was our first lecture. Then implement a deep neural network to solve the XOR problem, which is the second lecture. And then NLP with recent language models like transformers. So it's basically what we're doing, which is quite cool. So chatbots are a way for you to communicate to a machine that has access to large processable data without having the human component in between. So chatbots are also something that is coming up now more recently. One thing from the example in the beginning, word sense disambiguation, how can we find the meaning of words in different contexts? Again, here you have to try Java, it's so good. In English, Java can mean coffee, it can mean the programming language, it can mean an island in Indonesia. And here it's important to understand what a word in a context means to know what is the message of the sentence. Something that we're doing recently in our work is paraphrase detection. This is how can we find that different wordings mean the same thing. So when I say to you, Jan is going to the club or he is going to the club, that means the same thing, although the wording is a bit different. So the personal pronoun changed. And this is great for many applications like plagiarism detection. We want to understand that someone copied from another author, but maybe reformulated that sentences. So how can we detect that the information context or the semantic is the same, but the wording has changed? And that's paraphrase detection. There's many different dimensions to that, how you can estimate whether something is the same or not. So as a summary, there's 3 categories, basically. There's mostly solved problems, there's good progress, and there's still really hard stuff. So on the mostly solved stuff, there's spam detection. You know that from Gmail. You rarely get those messages like, buy Viagra now, or I'll get you 1 million from a Nigerian prince if you give me $1,000. So those things are categorized very well with NLP today. A part of speech tagging too. So what are the different grammatical components in a sentence? Is it an adjective? Is it a noun? Is it an adverb? And so on. And this always is a disclaimer. This is very well solved for English. So for other low resource languages like Arabic, for example, it might not be solved as well. Good progress we have on something like sentiment analysis. Is a sentence positive or negative? Is it, for example, a tweet about Ukraine war? Is it positive or negative? Does it have a stance? Word sense disambiguation, we've seen it before. To identify the meaning of a word is well solved. And machine translation recently too. You might know systems like DeepL that can actually translate to many different low resource languages recently quite well. And then the hard stuff is still something like question answering. How can I find the right answers to these questions? Even Google struggles sometimes to find the correct answers to your questions on these articles. Paraphrase detection and generation, something that we've talked recently about, and dialogue systems like ChatGPT. They seem very bright, but they also have their limitations still. So if you would interact with a human, it's still much different than if you would interact with ChatGPT. Okay, so let's move to the actual way, how can we use text in our deep learning models? And in the last lecture, we have seen a neural network that takes as input different features, we call them, in the input layer. This is just a recap from the last lecture. So for example, you have age, genders, how much sports they do, how many calories they take in. And we have this kind of mathematical formulation of a hidden layer that is a sum of the inputs times the weight matrix, and they get activated using some nonlinearity. and we call that entity that does that a neuron. And then we have the output layer, and that's our dependent variable. That's the thing we want to predict. So that's, for example, in this case, the probability of being alive. So given age, gender, how much sports they do, how many calories they eat, we can estimate quite well how probable it is that they are alive. So for text, this is a bit different. How do we define the features? So before we had some numerical variables, we had some things that we can pinpoint as a numerical formulation to make it in this mathematical expression. But now we have text, and how do we formulate text in this model? It's not that easy. So one of the definitions we make in natural language processing is the representation of text. So how do we want to categorize text? It can be on a character level, it can be on a word level. We can also say a phrase is our level of abstraction. And we call this abstraction a token. So a token is the high level of what or how we treat the text for processing. And there's different ideas. So one of the intuitive ideas is, well, text is just characters, right? We have an alphabet. We learned this in elementary school. And this has 26 letters for English. Let's not take any special characters, just A, B, C, D, E, F, G. And that's basically can be a scalar from 0 to 25. So before, when we had age and so on, now we can assign the word hello the characters from their alphabet, which is 8, 5, 12, 12, 15. And this is actually done. So this is a concept that is being used, for example, to find spelling errors in words. So if there's a character, if the neural network can detect a character that is out of place in a word, it can verify or it can overcome spelling errors. The problem here is that if you want to use it for larger contexts like books, there's much more combinations of characters that never occur related to the number of combinations that do occur. What does that mean? So if you combine all different permutations of characters, you get a lot of gibberish, and you get a very small percentage of words that actually exist in English language, for example. So that's a problem. We have a huge space of combinations of characters, but only very small percentage actually makes sense. So when the neural network tries to approximate this function of words, it will do this over a huge latent space that is useless, while there's only a small part that is actually useful. So idea 2 is, let's take all words in English language. There's a dictionary. We know Duden for German. There's also multiple ones for English. And they specify all the English words. Perfect. We have all words that exist. And that's around 1 million words. And there's also some words that don't exist, but people still use it. Let's not talk about them now. But let's say there's 1 million words. And now when we have a text or a book, we can assign each word that actually exists, again, a number. So now a sentence like, how are you, could be this representation. 12,398 is the position in the dictionary, okay? And now we don't have this problem anymore. We don't have this problem of having too many combinations of characters that don't exist. We just have the words that do exist. And you can incorporate special characters and all these things in there, and you will get around 1 million words for English. So one of the things that is still problematic is 1 million is still a lot to process. So it would be great if we could identify shared parts of these words that always occur in text to reduce that vocabulary. And what does that mean? So think about words that have an ending like ing. So words like eating, drinking, making, challenging, they all share common endings or stems. And when we have those common endings or stems, we can define subwords. And subwords are parts of words that reduce the number of the vocabulary by combining them together. So if I have 30,000 subwords, I can compose 1 million words in the English vocabulary again. And that's what we do here. So subword encoding or also byte pair encoding are methods that can be used to reduce the vocabulary, and then we end up with 30,000 of those subwords, and we can assign each position of the text a subword and combine them back to the original words. And also, it helps a bit with spelling errors. So if you have spelling errors, there can be common spelling errors. So for example, if there's specific keys on a keyboard that are close together, it's more likely that these spelling errors occur often. So if you have the default layout, R and T, for example, are common spelling errors, or L and K, because they lie near together on the keyboard. And if we define these subwords that have common spelling errors, then we can also use them to solve multiple spelling problems in the text. One thing that all of these methods have is out of vocabulary. So if there's a new character, a new subword, a new word that we don't know from before, let's say there's a new trend and someone invents a new word that happens regularly, then we don't know that word and we have to assign it a special number and say that's an out of vocabulary word. Okay, so now we have an approach to actually forward this into our network as a scalar value. But scalar values have two problems. So one is they're difficult to normalize. So if you have a value from 1 to 30,000, if we go back to last lecture, you would have to reduce, or you have to learn a weight that scales down 30,000 and another weight that scales up 1. So that's one problem. And the other problem is that scalars are one-dimensional. So there's not much space to learn representations and relations. And what does that mean? So if we look at the bottom right example here, ideally for the words that we define, we would like to have some spatial relationship. So for example, queen should be the same to women as king should be to men, right? The difference between queen and woman is the concept of them being a majesty. And we want to have the same concept between king and man. In one dimension, we cannot do that, but in multiple dimensions, we can do that. For example, here in 2 dimensions, we can do that to some extent. And the more dimensions we have, the more we can do that. So better would be, instead of a scalar, we assign a real dimensional vector of space x, and this vector represents the word space and also can relate words to each other. The dimension of this space basically defines the power that we have for these relations. So if we have a 3-dimensional space, we might be able to do this relation. If we have a 100-dimensional space, we can do 1,000 more relations. And we call this concept a word embedding. So a real vector that we assign to a word is a word embedding. Okay, that's important for later. Okay, some of the problems that we have when doing this is tokenization is language dependent. So when we split subwords or characters in English, we know how to do that to some extent. But then there's other languages like Japanese, there's Arabic, there's Chinese, there's different way of reading, there's different way of number formatting. So this is something we have to take care of. Then people use different formats for dates. They use different abbreviations. United States of America is sometimes US, sometimes it's USA. Source code has those great variable names that we have to take care of. So there's many different problems that we all don't care today about. But there is a lecture that does. Just we don't have time to do this. So just that you know, there exist more problems on tokenization. We just simplified it here. So if you do any NLP today, probability is high that you need a language model. So most of the applications, if you go to conferences on computational linguistics on NLP, they almost to 60–70% use language models nowadays. And language models are probability models to describe language. So language models have two key features. So one is they're predictive, which means they give a new token based on a previously seen context. So given that I say today we're going to do lecture, you would predict 11 because that's the lecture that we do today, and a language model would do that too. And they're explicative, which means they compute a likelihood or probability of a sequence. So given that I tell you the weather is sunny in winter, the language model would assign a lower probability than if you say the weather is sunny in summer, right? Because it's more likely that these words occur together. And as I said, most NLP applications build on top of these models, because once you understand how different words occur in the context, you can also understand different applications. Okay, so for example, in speech recognition, you would say that the probability of I saw a van, which is the actual thing that you want to say, is higher or much higher than I saw of an, which sounds similar, right? I saw a van, I saw of an. but that's something where the language model should assign a higher probability. And you can see that for many applications, this is true. And this definition of a probability just means we want to understand what of the text, what of the speech is more likely to occur. There are certain patterns in language that are likely to occur, and others are unlikely to occur. So here we want to learn, and that's basically also how humans learn to understand language as a kid. From our parents, we want to hear what is likely to being said and what is unlikely to being said. And that's basically how we come up to talk. So a bit more mathematically, the main task of a language model is to predict the probability of an upcoming word. So I give you a sentence, and I ask you, what is the next word? And then you give me the next word. And the language model computes over this vocabulary of, let's say, 30,000 words, a probability distribution. And for each word, it assigns how likely it is that this word occurs. So if I say, it's a nice summer day, today it is probably going to be, then it could be sunny, nice, a good day, but it's not likely to be a horrible day or horrible. Okay, so it assigns these probabilities to all the words. Some of them are more likely and others are more unlikely. So it's basically a conditional probability of a word, wn, given the sequence of previous words, w1 until wn minus 1. And one of the concepts that are very common in language models is how much we should look back in time. So basically, the more context you have, the better. The more of the previous probabilities you have, the better. And the more combinations of previous words you look at, the better. So if you can look at a context of only the previous word, that is not very useful usually, because it can be anything. If the previous word is, for example, an adjective or just let's say an article like a, it could be any noun that comes after that. But if you have more context and more connections of the previous words, that's more likely to be helpful for your case. Okay, so we're moving fast, but that's fine. We know what a language model is. Now we look at the state-of-the-art architecture for language models, which is the transformer. And today, almost all applications that have, all NLP applications are built on some form of transformer. So the transformer model in 2017 revolutionized all deep learning architectures for NLP. And now even applications from NLP to computer vision are using transformers. So this is a revolutionized concept. And it started with his paper, Attention is All You Need. And as you might guess, they introduced attention, which is a new way of computing layers of neural networks. So before we looked at feed-forward neural networks, now we're looking at attention neural networks. And the architecture that they propose is called the transformer. And it's built on attention, on self-attention to be particular. And in their paper, they use it for basically translation tasks, English to German and English to French translation. And later, it has been applied to many other tasks like word sense disambiguation and so on. One of the main benefits of this architecture is that it is highly scalable. Okay, it can parallelize very well among computational infrastructure. So if you would want to train a 100,000 parameter model or a 500 billion parameter model, you can parallelize that across thousands of GPUs, thousands of computers. And that's very effective because once you scale this architecture, you can solve more complex problems. Okay, so how does it work? We have some sort of input, like, for example, a French sentence. And then we have an output that we want. That's our target. And that's I am a student, the English version of that. And in between, there is the transformer. Okay, so more specifically, in between, there is two parts of the transformer. It's for one, an encoder. And the idea here is to encode the sentence in some sort of semantic space, like we've seen before, queen, woman, king, man. And this space has a semantic meaning to this input sentence. So it relates the words to each other's. And the decoder then takes that space and converts it into another text, okay? So this other text could be another language, could be another wording, like we've seen in paraphrase, could be other word meanings, like we've seen in word sense disambiguation, could be even speech again, okay? So we have some sort of semantic representation. That's like the truth of the text. This is the semantic content of the text right after the encoder. And the decoder takes that and says, hey, that's the content. Now I transform it to something else. It could be anything. It could be speech, could be another language, could be another wording. But I have this true value in the middle of semantic understanding, and that can be transformed into anything. And this true value is a mathematical space. It's a real value space in which these relations of words are being represented. And this is achieved through attention. We'll talk about it later, but that's the main concept. So the encoder and decoder both are different layers. So we have deep neural networks, so each of them is a number of layers. And as I said before, at the end of the encoder, the information is passed through the decoder through each layer, okay? So how does it look from an architectural perspective? One thing you know already, and that's here the feed-forward network. That's exactly what we've seen in last lecture, right? That's a layer of neurons, the sum of all weights times all inputs plus a bias, and then a nonlinear function. So this here is exactly that. And this here we'll talk today, self-attention. And then there's also one other part, is how we connect the encoder to the decoder. So how do we pass this semantic information, this space of word relations, to the decoder to generate new text, new speech, or whatever. Okay, so here's how it works. We've talked about this before. Each word gets assigned a word embedding. So that's a real vector. It's random, right? It's random. And this real word, the only condition is that the vector of this word is different than this word, okay? But this is random, this is random, this is random. They just have to all be different, and they lie around 0 for normalization purposes. And then we have some sort of mechanism that finds the relations between these words. We have a feed-forward network, and that's an encoder layer, okay? So 3 word representations, word embeddings for each word. They have some sort of mechanism to attend to each other, and then we have a feed-forward network. That's the magic there. And in between, we always keep the local history of words. So we always have this sort of perceptive field that this word here has some relation to another embedding here. It doesn't have to be exactly here, but it always has this local perceptive field that it is attended to, okay? So we keep the sequence through the network. And at the end, we have the same dimension as the input sequence, okay? Great. So there's 6 steps to transformers. First, we create word embeddings for each of the words. And we'll see that those are actually not 1, but 3. So we have a query, a key, and a value vector. Then we calculate a score between them to find this relation between words. We have some sort of normalization to stabilize gradient descent later. It's not too important. Then we use one of the non-linearities from last lecture, which is the softmax. And the softmax give us this probability distribution of scores that adds up to 1 again. If you remember, we'll have a recap on the next slide. But the softmax gives a probability distribution, the same that I just told you about, for each word of the input sequence. Okay, and then on this score, we want to keep those values that have high probability and discard others that have low probability, okay? So we take the values of the input and we multiply them by the softmax scores to keep the ones that are really probable and others that are not really probable. And then at the end, we sum up the weighted vectors, and that produces the output of the self-attention. So how does it look like? It's actually quite simple if you look at this figure. So the query, the key, and the value, they're all word embeddings, okay? So for a sequence of 3 words, you have 3 query vectors, 3 key vectors, and 3 value vectors. The first thing you want to do is you want to take the query and the key. So the query is we ask, does this word relate to another word? The key is identifying the word, okay? So let's say I have the sequence, I like cake. I have the query of I, this is an embedding, and I have the keys for each of the other words. So I use the query of I and say, how much does it relate to the keys of the others? And this operation here with the softmax, so we multiply them, we scale them, there's a masking operation, it's not too important, and we have the softmax. This is important. This is the probability distribution that tells us how much do they relate to each others. And then we want to say, okay, and the ones that relate a lot, we take the actual value from them and we pass them through the next layer. So the first thing is identify how much they relate through the query and key, and then take the ones that relate a lot from their actual values. Okay, and just to remind you, the softmax the formulation is quite easy. It's good to remember this by heart. It's e to the actual one that you look at, the actual neuron or word that you look at, e to the score of that, divided by the sum of all of the exponents. Okay, and you always get a sum to 1 distribution. And you can formalize the figure here on the right also. It's the softmax of the query times the key transposed divided by a normalization constant times the value. That's one matrix operation. Here you can also see that a bit more visualized. So here is the queries times the keys, and that will give you the raw scores. You normalize them with softmax and this normalization component, and you multiply them times the actual value of the word to forward them to the next layer. We actually have an example here. So I like cake. This is actually the example. I like cake. You have the query of I, you have the keys of all of them, and you have the values of all of them. And now what you do is you compute the query of I with all the keys of the others, and then you multiply them by the values with a softmax. So the ones, before I said the ones that are more relevant, so the score that is high will forward high values, and the score that is low will forward low values. And then so you get 1 score for each of these word relations. Okay, I think we talked about this. Yeah, so there's 4 more things. Self-attention, I think we talked in detail. 3 more things. Positional embeddings help us understand at which position a word is in the sequence. Imagine, oh yeah, sorry, there's a question. Yeah. Right. So if you don't have a, sorry? Yeah. So the key doesn't represent the position, but it represents the identity of that word. So imagine you have a really long sentence, like thousands of words, and you would compute this key times the query and then the value. You would lose track if that word was either in the middle or somewhere at the end or at the beginning. So this positional information helps to better understand the exact position. There is a lot of redundancy in transformers. That's a critique, actually. So it's a great question, a critique of these models. And we try to reduce that complexity now because these models get huge and there's much redundancy, as you said. But in this particular aspect, the positional embedding that we talk now is more a way of finding the exact position in the text rather than finding the identity of the text. So there's this small differentiation, I would say, but you're totally right. There's like huge redundancy, and we'll talk about this later. Thanks. So positional embeddings help us to identify where it happened, and then nonlinearity and scaling help us to reduce the problem of this gradient explosion that was in the last lecture, and to, scaling is very important, to increase the embedding dimension. Remember before, when this queen-king example was there, the higher the dimension is, the more complex things we can represent. So the more complex relations we can make. And the feed-forward and scaling part is basically there to scale up from 700 dimensions to 2,000 dimensions and then back again. So we have a larger space to represent. And masking is a way to make basically everything faster, because let's say you have a sequence of 100 tokens, you don't want to compute the attention for 500 tokens, right? So if you have a standardized context of 500, you mask the remaining part and you just make it more efficient. Okay, so we talk about self-attention, and self-attention is great, but we want to learn multiple of these self-attention layers at the same time. Why is that? Let's say one of these self-attention layers that we talked about learns the relation between king and queen, man and woman. That's great. but we wanted also to learn multiple features at the same time. Maybe another layer would learn the relation between Python and deep learning. Another layer would learn, so they all have their specific parts that they learn in the network. And on a higher level, they could learn different tasks. Like one layer would estimate the sentiment of this sentence. Another layer would estimate the word meaning of that sentence, and so on. So it gives the attention layer multiple, what we call representation subspaces, to learn different things on this model. And how that works is basically that you stack this layer into the depth dimension multiple times. So for example, 8 times. And then you basically compute the same thing, the same formula we had before. And there is a trick, we will see that in the notebook, how you can do it a bit more efficiently by one matrix multiplication. So imagine that this query key and value are just now stacked matrices. And if you compute them, then you can just do it in one operation. And matrix multiplication is super optimized. There's like decades of research on that. So it's very optimized and it's very fast. Okay, yeah, some of the things that additional are occurring here. We had this in the first lecture, residual connections, very easy concept, but super effective. Take the identity of a first layer and forward it to the next layer. This way you overcome gradient problems. So you can, if you imagine, if you have still this figure from the last lecture where we backtrace the gradients, you can see that, can you see the mouse? Yeah. You can see that here you would have to pass all the way through the normalization, feed forward, normalization, multi-head attention, and so on back to the first layer. But using the residual connections, you would have a split here. You would take the normalization, and then you can directly go to the first layer, and you can here directly go to the first layer again. So you bypass some layers, and the gradients don't get reduced. The positional encoding comes right after the input. So you have your sequence, and what they do is they take like a sinus function to represent that some of these are the beginning tokens, middle tokens, and end tokens. So it's a continuous space throughout the network. Okay, normalization, we talked about this briefly. It's not too important. I mean, it's just a way of scaling these attention layers and not having too large values that then lead again to too large gradients or too small gradients. Okay, so how does it look like? I gave some examples, but this is actually visualized attention. Okay, so each of these colors represent a different head of the multi-headed attention. So this is one attention layer, and they learn different things. So for example, it in the sentence, you can quickly read the sentence if you want. The animal didn't cross the street because it was too tired. So in one layer, the yellow one, it relates very much to the animal, which is expected. That's our first intuition, right? It is the animal. But in another attention layer, this also relates to tired. So it found the dimension that the animal is tired and it is tired, okay? So yeah, so the animal is it in the same sentence, but also there's a relation between the animal and tired. And this is like a cross relation because it is the animal and it is tired, okay? So different parts of this multi-headed attention find different features in our text. Here's another example with more attention layers where it relates to many things in this sentence. Okay, yeah, summary of the architecture. So the encoder is processing the input, and now we're moving to the decoder part. Maybe, yeah, next slides, this will come again. So the encoder we have done, so to say, and now we have this part of, now we have the representation, and we move it to the decoder to generate actually text or speech or whatever we need to generate or we need to translate to. So one key thing between decoders and encoders is that encoders take a two-dimensional or two-sided context into account. So you have left to right context and right to left context, while a decoder only attends to the earlier positions of the input. So if I give, let's say, I don't know, a sentence of I like cake and go to the park, then for the encoder, you would have both sides of this sentence, while the decoder only gets the left-right context. And that's the key difference, because when we generate text, we don't want to see what comes next. Even though we knew what came before, we want to generate on a basis of only the previously seen text. Okay. And then one part that is important between the encoder and decoder is another attention mechanism to tell the encoder and the decoder what information to attend to from the encoder. Okay, so here the encoder-decoder attention is similar to what we've seen before, to the self-attention or multi-headed attention, but it creates a query matrix from the layer below and takes the keys and values from the output of the encoder stack. So on the last encoder, that's the last layer of the encoder network, you have like 6 layers, we now attend the queries from the layer below and the keys and values from the output of this stack, okay? And we do this for all decoder stacks. We don't just do it for the first one, we do it for the first, second, third, fifth, and so on. And that's basically how both of these components work together. And by the way, we'll see this later, but architectures on transformers don't have to have both. So some models, they have encoders and decoders, some only have encoders, others only decoders, and there's different reasons why we would do that. Okay, I have to rush a bit because we're a bit short on time today, unfortunately. So yeah, encoder will provide the material. You'll see more detail how that works. But just to summarize the architecture, so we've seen on the left side how the encoder works. We've seen on the right side, to some extent, how the decoder works. And the last part of the decoder is, again, a softmax of the output probabilities of a word. So if I give a sentence, I like cake, and I want to go to, then you get a probability distribution over the entire vocabulary, and the word with the highest probability, this is the one you choose, and this is the one the decoder generates. We've seen multi-headed attention, which is in both the encoder-decoder. We've seen the self-attention, and we have seen the cross-attention between encoder and decoder, which is a modified version of the self-attention. Okay, so what can we do with this? There's many models built on transformers, and one of the most popular ones is called BERT. BERT stands for Bidirectional Encoder Representations, so this is an encoder model. And one of the trends that we've seen in recent years on transformers is to pre-train models. And what does that mean? A pre-trained model means a model learns basically to understand the intrinsics of language. And if we have a model that understands the intrinsics of language, we can easily adapt it to other tasks. So before, what we would do is, hey, we want to solve sentiment analysis. We want to know if a sentence is positive or negative. What we would do, we take a model, we take a data set on sentiment analysis, and we let that model learn on this data set. And it works fine. But what is a better approach? Instead of learning that model on this task specifically from scratch, we can take a model and learn on general language. So we take books, we take web articles, we take news articles, and we let that model learn how the language works in itself. And in the next step, we only need a smaller fraction of the sentiment analysis data set because most of the language features are already learned, and we can just transfer it there. So we bypass, for one, a very expensive operation to learn a problem in this language from scratch. And so we reuse this model. And another part is that on the sentiment analysis task, we can perform better because the model already understands the language beforehand. And this is very useful also for different languages. So imagine you would have a very limited amount of data for Arabic or for Japanese or even German. It will be difficult to perform this task of sentiment analysis because the model doesn't understand the intrinsics of German language. While if you have a model that already trained on German language, that model will be much more capable to solve this task with little data. So pre-training is key here. And we have 2 phases. The pre-training phase is this general language learning, and the fine-tuning phase is this adaptation to a specific task. So this is actually solving the problem we want to solve. And yeah, pre-training is expensive, but we only have to do it once. So it takes billions of tokens from web text. Nowadays, it's basically the entire internet. It's multiple 600 terabytes of text data. And we do that once. And then we go to a cheaper training phase where we just learn the task. And that just needs a few thousand to million tokens then. Okay, so BERT has 2 pre-training tasks, and masked language modeling is the most important one. And there's also next sentence prediction, but that's not so important.
And mass language modeling is a way to do language modeling, like we've seen before, to estimate the probability of a word given context. And what they do is they corrupt the sequence of texts with specific mask tokens and then predict these mask tokens. So you have a sort of bidirectional language model. You can mask any token in the middle and not just the ones to the right. Remember before it was, I have a sentence, predict the next word. What BERT does is, I have a sentence, predict some words in between. And then next sentence prediction that just says that, given a text, is this the next sentence or not? So if I say, I went to the park and I had a lot of fun, this can be the next sentence. But if I say, I went to the park, I'm flying to Chicago, this is not very likely to be the next sentence. Right, so we have, instead of left to right context, we have a bidirectional context. So we take into account both directions of the text because we're masking things in between. And we can also formalize this by saying that the probability of a word given the context W1 to Wi-1 and the probability of the context from the right, which is Wi given Wn to I+1. Okay, so all the words from the left and all the words from the right. So what they do is they take a book's corpus and some Wikipedia texts, and they take 50% of the words in that text and replace it with a mask token. So now you have Wikipedia and books with text that has 15% of these mask tokens. They're just replaced. So you can still read it as a human, but some of these words, they're just masked and they don't make sense to you anymore. And the idea is now to predict what have been the original words given that context. Okay? And why is that important? If we do that, the model understands how to fill these gaps. And that basically gives knowledge about which probabilities for which words are appropriate in these texts. So how they do this, on each of the embeddings, they add a small classification layer. It's just a feed-forward network that takes the dimension of the embedding and converts it in the dimension of the vocabulary. So the output is the dimension of the vocabulary, and each of the values of the vocabulary has a probability for the word. And we take the highest probability and say that's the mask token replacement word. Okay. And again, this is using a softmax. I mean, you will see that throughout the lecture, it's always a softmax. So more specifically, to visualize this, the professor gave the exams to the students in the class. We masked the tokens. So now the text looks like this. And this is done for the entire Wikipedia plus some 40,000 books. So two things that you have to consider. Why did they use 15%? Well, they experimented and have seen that if you do more masks, it gets complicated to replace the words. There's not enough context. And if you are not masking enough, then it's too expensive to train. You have to do many iterations to get the probabilities right. So even if I would mask more words in this context, it will be difficult for us to say what is the right word. So even here, there's multiple ways that could fit here. It's not only exams, right? And here, it's not only class. But the more you mask, the more complicated this gets. Okay. The other task is next sentence prediction. And here, we basically take the entire documents from Wikipedia and the books corpus, and we take 50% of them having the actual next sentence. So we just keep it like it is. It's sentence and next sentence. And on the other 50%, we take a random sentence from another document, okay? And the likelihood that this is the next sentence is 0%. So we have 50% where the likelihood is 100% and 50% where the likelihood is 0%. And then we predict, or let the model predict, is it the next sentence or not? So here's an example. Sentence A, Jane was in the store. She bought some groceries. That's the next sentence. And then the other one is Jane was in the store. The answer is 42. That's not the next sentence. And the model learns the label is next sentence or is not next sentence. Very simple. The problem here is there has been, so BERT has been released in 2018, and there have been several studies showing that this next sentence prediction is not as useful. Does anyone have a guess why? Why it's not yet that useful? Mass language modeling seems very complicated. So anyone has a guess why it's not so useful? Okay, yeah, it's too simple. I mean, anyone can do it. So it's not that difficult to do. And if it's not that difficult, you don't learn from it, right? So if I give you very unchallenging notebooks and unchallenging lectures that anyone can understand all the time, it's probably not giving you anything to learn. So the same thing is true here. If I give two sentences that are super unrelated, anyone can say they're not related. So although there is some value in some applications, most of the times it's not very, very relevant, this task. Okay, some technical details, how the model processes the input. We have a specific CLS token that helps us later in fine-tuning phase to have a representation for the entire sentence. So if you want to classify a sentence to be have a positive sentiment, you would use that specific token that we introduce to represent the entire sequence. So instead of using individual words, we use this token, the CLS token that we introduced, or like they introduced, but we use it to identify the sequence. And then there's a separator token to separate multiple sequences. Let's say you have one sentence is the first sentence and the other one is the second sentence, and you want to see if they are entailed or if they're similar, you would separate them using the specific separator token so that you can say those are not parts of the same sequence. Okay, yeah, and let's maybe look at an example. It's easier to visualize. So here, the input would be CLS token comes first, and this CLS token is there to represent our entire text. Then we have the first sentence, my dog is cute. And then we have the separator token separating it from the other sequence. And this is he likes playing. And now the task could be, okay, let's find if they are related. In this case, they are related. So what would happen is we have the token embeddings. Okay, those are the query key value we've seen before. Okay, and then we have segment embeddings that help confirming the separation. So we have one embedding that identifies the first part of the segment, A, and the other one, B. And those are, again, random, but they have to be different. So if you imagine this in a multidimensional space, you would say you shift all of the embeddings that are in A to this direction, and all of the embeddings that are in B to this direction. So you have a more separation between them. And the position embeddings we talked about, they're there to say, this is the first part, this is the second part, this is the third part, and so on. So where is the text in the sequence? And all of this together composes the final embedding that is passed through the network. Okay, BERT takes transformer encoders only. So it's an encoder-only architecture. It has self-attention. Yeah, it's basically a single network that is trained on books corpus and Wikipedia. It's only 16 gigabytes. There's iterations on BERT like Roberta that take 160 gigabytes. Now there are models that take, as I said, multiple tens of terabytes of text. And there's two versions. BERT base takes 12 encoder layers and 12 self-attention heads, and large takes 24 layers and 16 heads. And this year has 340 million parameters. And this year has, I think, around 500 million parameters, it must be. So 500 million. ChatGPT, as a reference, has 8 billion, for example. And GPT-3 has 170 billion. So they're much more, they're growing much more than BERT. Okay, and then once you pre-train this using mass language modeling and next sentence prediction, you can then do a variety of tasks. For example, classification. You want to say if two sentences are related or not, yes or no, we classify them. Question answering, you want to say, given a text, given a question, what is the answer? Named entity recognition, you want to identify the parts of the text, the adverbs, the adjectives, and so on. Oh no, that's wrong. Named entity recognition is the actual entities, the named entities that you want to extract, like, for example, a company name or something. And how that works is you have here on the left the pre-training with the mass language modeling and next sentence prediction. And then when you're done, you move to the right where you modify the model's components in a way that they solve the task. So for example, if you have a question answering pair, you want to identify, given a question, where is the answer of the text? And how you modify this is instead of having these token embeddings on the classification layer, the classification layer on the classification token, you would have the classification layer on the token embeddings, and they would give you the start and end span of the text where the question's answer lies. Okay, so key takeaways, model size matters, so the bigger, the better. Okay, BERT large is 340 million, BERT base is 110 million parameters, and now models are getting to multiple 100 billion parameters. More training results usually with higher accuracy. The more pre-training you do, the better the model is used for other tasks. And also one key thing is that bidirectional approaches like mass language modeling converge slower than left to right approaches. So if you generate the next word is a bit faster than if you predict the words in two contexts. Okay. So what is the time? Okay, let's see. We'll do a quick version of GPT just to go to ChatGPT then. So GPT is decoder only, so there's no encoders. BERT was encoder only, GPT is decoder only. And the thing is that encoders have bidirectional context, so language modeling is simply not possible in our standard formulation. You cannot predict the next word with BERT, okay? And that's a key disadvantage. You can make many classification tasks, many question answering tasks, but what you cannot do is to generate text with BERT, okay? So you can replace words, but you cannot generate words. And that's where we need decoders, okay? So yeah, we need to go a bit faster. So why not use it for everything? Because we cannot generate one word at a time, and we cannot generate stories, we cannot generate new text, and that's what we need for chatbots, for example, or translation systems. So what GPT does is given a sequence up to a certain point, and we might know the rest of the sequence, okay? We might know word 5, 6, 7, 8, 9, 10, but we don't provide it to the model. And that's the key difference. In BERT, we would provide it to the model. In this GPT architecture, in the decoders, we provide it only unto a certain degree, and then we predict the next word, and we take that word and forward it back into the model, and we do this step by step, okay? So given the first word, like robot, we give it to the model, and it would generate the next word, must. We take that word and forward it back into the model. And we do that multiple times until we have generated the sequence. So GPT defines also some special tokens, like the start token and the end token. The start token says, here's where we start. And the end token is there for GPT to generate it when it thinks we're done. Okay, so when GPT generates the end token, then we're done. The text is done, okay? Otherwise, it would generate forever. Okay, GPT-2 and GPT-3 are iterations on GPT. To be honest, there has not been much innovation in terms of model architecture, but more in terms of scaling the architecture. So GPT-2 and GPT-3 scale this to more parameters, to more data, to more computational architectures, computational infrastructure. And now these models are becoming very large and very impressive, but the core architecture has remained mostly the same. So here's just a quick comparison between GPT-2 and BERT. So as we said, the one is stacking decoders only, the other one is stacking encoders only. So the question is, what about encoder-decoder models? We've talked about this in Transformers. For this, we have extra slides, which I would not be able to go over now. But those applications are, for example, for translation. So you have some encoder that encodes the one language into a common space and then generates word for word into another language. That's an application for encoder-decoder. And there's models like T5 that, here's a bunch of slides, but I will not be able to show them today, unfortunately. So let's move to ChatGPT directly. Yeah, ChatGPT relies on GPT. So we can see here that I have asked it to create a poem about deep learning. So probably now everyone reads the poem and doesn't listen anymore. So maybe we can actually do a demo. That would be cool if it works. Yeah. So anyone has any query to send to ChatGPT? Okay, now it's not working. Too many people use it. Yeah, that was my mistake. Okay, so let's go back. We have some model that you can interact with in language, and you can ask it basically everything. It is trained up to a certain time point. So why is that? Because the model that it relies on is GPT, and GPT is trained with data in the pre-training with data up to, I think, 2022 or 2021. So it has knowledge about text up to that point. So they take the GPT model and modify it in a way to make it good for dialogue, to make it good for chat. And since they don't want to pre-train the model all the time, which is very expensive, it only has knowledge up to a certain degree. So if you ask it about recent events, it probably won't be able to answer. Okay, So it solves conversational problems of GPT. GPT is not good for conversation because it's not trained to do so. It's trained to generate the next word of a text. So if you ask GPT or GPT-3 a question, it can answer to some extent, but you see that it just replicates how a text with questions would be, would occur in online text. So maybe in blog posts, there's a rhetorical question, and then there's more text below that. And that's basically what GPT reproduces, because we trained it to predict the next word given internet text. And ChatGPT, on the other side, is more like a human. It does a conversation with you. It answers your question. It goes into the points of your question, and so on. So the key point here is we're missing basically a way to do dialogue. And what better way we would have than asking humans how to do dialogue, or just having interaction with humans that do dialogue like we do. So how ChatGPT works is we take this massive model of GPT as a starting point because it learned how language works to some extent. And then we have 3 steps. So the first thing is we want labelers, human labelers, to tell us what would be good answers to questions. So we give questions or prompts, we call them in general. They don't have to be questions. They can also be describe deep learning to me. That's more of a prompt. We give these prompts and we ask humans what would be a good example of an answer to this. And humans are particularly good at this, at least what we think. And then we have the answers to this. So the first step is to take prompts and answers and then fine-tune GPT-3 to follow these prompts and answers. Okay? One problem about this is it's not very scalable. You need millions of humans or human answers to these questions to make it scalable. Otherwise, you learn a very small and narrow set of answers. So how can we make it more scalable? And that's the second step. Now we train another model, and we compose another model, and that model's only goal is to say what is a good answer and what is not a good answer. Okay? So this is the reward model. This model tells us if one of the produced things from ChatGPT or from GPT-3 is a good answer or not. And how we train this model is a bit easier. We don't need to generate all the answers by humans, but we ask humans to rank what are good answers. Okay? So now, instead of generating answers directly, we take GPT, we can generate millions of answers with it, and now we ask humans to do a simple task. Hey, here are 4 answers to this question. Can you rank them best to worst? And the human ranks them. And we do that for some hundreds of thousands of examples. And then the idea now is to scale it from 100,000 examples to billions of examples is this reward model. And the reward model does one thing, it ranks the answers again, but now in an automated fashion. We don't need the human anymore. So in the third step, we generate answers with ChatGPT, and now we would have to rank them with humans again, but we have this reward model trained, and we don't need humans anymore. We take the reward model, and the reward model tells us, hey, this is a good answer, this is not a good answer. And with these answers from the reward model, ChatGPT can learn completely automatically and say, here are 4 answers. The reward model says, this is a good answer, this is not. And the model says, okay, fine, I'll make sure that next time this is a good answer and this not. And again, I generate 4 answers, and this goes back and forth between the models. So the goal is, first, humans need to tell us what are good answers. Then ChatGPT needs to understand how to rank answers. And the reward model tells us what are good answers and what not in an automated way. So this is to scale it. Okay, DALL-E, we'll not talk about this. Yeah, thank you very much. I think we're good on time then for the last talk. Okay, maybe a little bit late. But thanks so much. The slides have more details. There's more details on T5, on DALL-E, on other technologies. So you can go deeper, and there will be a tutorial recorded in VS Code where we implement BERT from scratch. So thanks very much for listening.